Hello, a very warm welcome to everyone here and those of us who are joining us via Zoom webinar. Thank you for joining us for this mathematics masterclass on why linear algebra is important. Now, before we begin, there are some housekeeping announcements. Please adhere to the safe management measures. Maintain a safe distance of 1 meter apart. Please sit in the designated seats in the LT, and please keep your masks on throughout. In the event of an emergency, please follow the directions of the ushers and evacuate in an orderly manner. We also kindly remind everyone to please put your phone to silent mode. At the end of the masterclass, please exit the lecture theatre using the door on the right of the screen. There will be a Q&A session at the end of the masterclass, but feel free to send in your questions via the QR code here on screen and visit the pollev.com/Q&A-LT27. That is pollev.com/Q&A-LT27. For those who are joining via the webinar, in the event that the Zoom session ends or disconnects unexpectedly, please rejoin us at the same link. So before we begin, let's share a trailer on the mathematics department here at NUS.
Maths major. #maths.
Why maths? Because it helps you think conceptually and rationally. Exactly what the digital future needs.
There's so much data out there today. Maths can actually help us in real life to tackle complex problems.
If you enjoy exploring new ideas, maths is your major.
When I was in JC, I was very intrigued by Galois theory, and now as a maths major, I get to explore his ideas in depth.
As a maths major, you'll take these core modules plus the option to pursue a specialization of your choice.
The curriculum does 3 things. 1, to prepare us for careers. 2, for postgrad research and academia. And 3,
Inspires fascination for maths.
Maths majors see abstract ideas in everyday objects. My interest is in group theory. It's vast, with opportunities for research to take ideas one step further.
So again, why maths? It opens doors into finance, government, or be a multimedia architect.
now you can be involved in solving complex challenges.
If you start right here,
Okay, hope that you all enjoyed that small trailer on what mathematics is like in NUS. Today, Associate Professor Victor Tan, who is the Deputy Head of Teaching at the Department of Mathematics, will elaborate on the importance of linear algebra, the basic concepts, and its wide application to computer science, engineering, data science, economics, and many other disciplines. Prof Tan is also the president of the Singapore Mathematical Society and organized a wide range of mathematics enrichment programs for school teachers and students. So without further ado, I would like to invite Prof Tan to continue to conduct the masterclass. Thank you.
Okay, good afternoon, a live audience in this LT, as well as all those who are watching on Zoom. Yeah, thanks for Xuanru for introducing me. And yeah, he also mentioned the title of my talk, why is linear algebra important? Actually, the title of my talk is very long. There are 2 parts. So the second part, I think the organizer just ignore because it's too long. So actually, more importantly, I would like my audience to know why should students not study linear algebra? Okay. So once again, if you have any questions, and you just now you missed out the QR code for the Poll Everywhere link. Yeah, don't worry, I'm going to show it on every slide. So as and when you have a question, you just scan the QR code and ask a question. You can ask questions about the talk itself or about the mathematics program. Okay, so let's go. Yeah, do you know that you are now sitting in this LT27, which is actually the largest LT in the whole of NUS? How big is this venue? You can take almost up to 700. So it looks like very empty today because of safe distancing, we only allow 80 people. So it's slightly more than 10% only. Now look at this slide. This is my linear algebra course before COVID, okay? Precisely in this LT. Yeah, I miss those days. Yeah, now I also Zoom for my classes. So you may be wondering, how come mathematics such a big class? Well, mathematics major, of course, they will take linear algebra, but linear algebra is not just for math major, okay? It is very useful. That's why students from many other majors are also taking my linear algebra module. Okay, so this is the fact. Mathematics uses linear algebra, but linear algebra also will be used for computer science, machine learning, engineering, statistics, econ, finance, data analytics, and many, many others. Okay, so just now the previous slide, what you see, other than the math students, I also have the data analytics students, finance students, computer science students in it. So that's why we occupy the entire LT. I also have a separate linear algebra course for the engineering students as well. Okay, so yeah. So today I'm just going to show you a few examples how linear algebra can be applied in real life. Okay. But first thing first, what is linear algebra? Two simple words, right? Linear and algebra. Probably algebra, you know, right? Many students probably think algebra is mathematics. Mathematics is algebra. Yeah, but not quite. Algebra is just one area of mathematics. There are many, many other areas. If you come to university, if you major in mathematics, you're going to find out that there are many different areas of mathematics. But I'll come to algebra later. The key word is actually linear. What is linear? Linear comes from a simple word. Which word? It comes from the word line, right? Right? Linear is the adjective of line. Yeah? So in other words, this is the word that describes something that has the property of the line. But what do I mean by that? What do you mean by property of line? Okay, let me make it more explicit. One-dimensional linear object is what everybody is familiar with. That is a line. But I want you to get this. In mathematics, when we say a line, we refer to straight line. Okay? So if you say this is also a line, that is wrong. Something that is like a curve, like a rubber band, or like a string. This is not a line. In layman, of course, we use line, the word line loosely. But in mathematics, when we say line, we mean straight line. We don't even need to emphasize straight line. When we say line, automatically we mean straight line. We mean straight line. Okay? Okay, so this is one-dimensional linear object. But we don't have to stop at one dimension. What is a two-dimensional linear object? Very good, huh? A two-dimensional linear object is a plane. Again, if you go and tell layman or non-mathematics people, when you say plane, they may think of, first thing they come to their mind is aeroplane. But when you are in a math class, automatically you will switch, right? When we say plane, you know, we are referring to something like a sheet of paper. Once again, when it is linear, it has to be flat. It cannot be something like this. It cannot be like a blanket, right? You can bear, or you can, you know, do anything you want. Yeah? So linear is something straight, something flat. Okay, so if you get this idea, then linear algebra is the study of mathematical objects and properties that are related to lines, planes, and their generalization. So what do you mean by the generalization? You see, so I say that line is one-dimensional, plane is two-dimensional. But what about three-dimensional, four-dimensional, and so on and so forth, right? So the higher dimension is the so-called the generalization, something that beyond our intuition, something that what we can visualize anymore, right? If you go to five-dimensional, we can't really draw it, we can't really see it, but we still can learn it through algebra. That's why this is called linear algebra. Okay? And the mathematical objects that students will encounter when they are studying linear algebra are what? Linear system, matrices, and vectors. I believe if you come from A level or equivalent, you must have learned vectors before, right? So you're not entirely unfamiliar with linear algebra. You already know what is vector. Some of you may also learn matrices. Linear system, later on I'll show you. It is also something that you have seen before, except that you don't call it a linear system. Yeah, but I will show you in a while. Okay, but before that, I want to further use a very simple example to see why every people are so feel that linear algebra is important. So why linear? So I'm going to show you this. Now, everyone know that this is not linear, right? Yeah, because it's a curve. Now, suppose I ask you, can you find the length of this curve? What would you do? Okay, very good, huh? Yeah. Oh, so he can anticipate what I'm going to say. But before that, suppose this is something that is flexible. And if we ask you to find the length of this object, the simplest way, what you're going to do is you straighten it, isn't it? Yeah? You are going to turn something that is non-linear to linear. Why do you do that? Because it's something natural to do. When it becomes straightened, you can either use a ruler to measure, or mathematically, the formula, the equation is also simpler to measure something that is straight rather than something that is nonlinear. You agree? Okay, so this come to where our friend said just now. Suppose this is not something flexible. You can't stretch it. It has to be like that. Of course, one way, for those of you who learn calculus, probably you say, I use integration, find the arc length. Wow, only so complicated. Especially if you are going to apply this to real life, what you are going to do is, you do approximation, isn't it? You try to divide this whole thing into smaller parts, and each smaller part is almost like a straight line. It's almost like linear. Okay? Now, in mathematics, this process is called linearization. Yeah, you turn something not linear to linear. So you see, why we do that? Because linear is much simpler. Right? If you have a non-linear equation, there's no guarantee that you can find a solution easily. Yeah, but if it's linear, everyone, if you recall a line, it's very easy for you to find solution. Okay? So remember just now the three items that I said that you study in linear algebra: vectors, matrices, and linear system. So I'm going to go through it very quickly. So the way I'm going to introduce vectors and matrices is in terms of their dimension. Okay, for starting with 2 dimensions. So a 2-dimensional vectors algebraically looks something like this. Some of you may say that it doesn't look like what you learn in, say, H2 maths. Yeah, because you for vectors you probably use 2i plus 3j plus 7k, something like that, right? Yeah, but that notation is more for physics, more for engineers. When you are in linear algebra course, we usually just use a pair of numbers and close by brackets. Okay, so get used to the notation. Huh? So the most important thing are the 2 numbers involved. However we want to present it, it doesn't really matter. Yeah, but the convention in the linear algebra course, a vector will look something like this. And you know, for a 2-dimensional vectors, we can actually draw it, right? We draw it, we represent it geometrically by an arrow. We draw an arrow on the XY plane. Yeah, still remember your A-level? H2 maths. Okay, what about matrix? Okay, I'm just going to simplify things a bit. So let's say 2 by 2, we correspond it to a 2 by 2 matrix, 2-dimensional. Okay, that means 2 rows and 2 columns. So again, there are numbers within the bracket, but this time there are 2 rows, 2 columns. So we call this 2 by 2. How do you represent a 2 by 2 matrix geometrically? Can you draw on it? Not exactly, but you can describe it. Okay, a 2 by 2 matrix can serve as a transformation that transforms one vector to another vector. Now, the concept of transformation means that you have an input versus an output, right? Before and after. That's called transformation. Yeah. So let's say you take the red color arrow as the input. Then this matrix, this 2 by 2 matrix can, in some way, yeah, turn it into another vector. Okay, so this is what I mean by transformation. Now the transformation can be as simple as like a reflection or rotation or scaling and so on and so forth. Okay, so yes, so 2-dimensional vectors and matrices can be described algebraically, geometrically. Let's come to 3 dimensions. We can do something similar, right? For 3-dimensional vectors, algebraically, that means it has 3 components, 3 numbers instead of 2 numbers. Yeah, and geometrically, it's still the same. I can still draw an arrow in the 3D space. Yeah, 3D space, just add one more axis, x-axis, y-axis, z-axis. Yeah, and for a 3-dimensional matrix, a 3 by 3 matrix, again, it has the same kind of geometrical property. Namely, you will transform a 3-dimensional arrow to another 3-dimensional arrow within the 3D space. Okay? Now, here comes the important point. When we go beyond 3 dimensions, can we still describe vector and matrices geometrically or not? No. Our intuition is only up to 3D, right? Now you go to 4D, 5D, you can't describe things geometrically anymore. So you can't really use geometry to study linear objects. That's why we learn linear algebra. You see how easy is it for us to just extend it to 4-dimensional vector, 4 by 4 matrix, and so on and so forth. There's no limit, isn't it? Right? So you may be wondering, what for? It's something abstract, right? 4-dimensional, 5-dimensional. You can't even draw it. Why bother? It's not real. It's abstract nonsense. Okay, but if you think about it, vectors are not just used to describe arrows. It actually goes beyond 2 and 3 dimensions. Vectors, the power of vectors is that we treat the numbers inside the vectors as data. All right? So sometimes we need to package 5 or 6 components, 5 or 6 numbers within a bracket, within a vector. So that's why you are going to have 5-dimensional vector, 7-dimensional vector, and so on. Okay? So it's not just something physical. Yeah. The power of linear algebra is really that it can apply to any dimension. All right. Now, remember the third object in linear algebra is a linear system. And just now I said, linear system actually is your old friend. You learn it even before A-level. Secondary school, you already learned this. Look at this. You don't call it this linear system, you call it simultaneous equation, isn't it? Way back in your secondary school. Yeah? But this is actually an example of a linear system with two equations and two variables, x and y. And recall, when your teacher gives you such a two equation, what she expect you to do? Yeah, and then try to solve. Okay, I don't want everyone to shout out the answer, but I mean, mentally you can, I think very easy for you to find out what is x and y, right? Even without writing it down. Okay, let me review the answer straight away. So for this case, for this system, x is equal to 1, y equal to 0. Right? We call this the solution. Now, for a simple 2 by 2 case like this, we actually can describe it again geometrically. Yeah? Each equation represents a line, isn't it? This is the equation of a line on the xy plane. Yeah? So two equations, that means two lines. And when you draw two lines, they intersect. So the intersecting point is precisely the solution of this linear system. So the whole thing is very nice, right? You can solve it algebraically. You can also interpret it geometrically. But now, suppose I generalize it again. Look at this example. This is a linear system with 5 equations, 4 variables. How do you find the solution? Yes, you can find if you are persistent, and you have one whole day, you can do it. But in linear algebra, you will learn a systematic way of solving a huge system with any number of equations, any number of variables. And you see that in this case, there's no longer any geometrical interpretation, right? You can't say it is a line anymore. Yeah, it's not even a plane because it's more than 3 variables. Yeah. So let me just give you start with a simple example of heat transfer, which I think everyone can easily relate. It's like a thermal physics example. So even if you don't take physics, doesn't matter. I'm sure you can understand this. So I want to study the temperature distribution on a thin plate. So imagine this is a thin plate. Yeah. So it doesn't look like a mathematics question, isn't it? Yeah. Okay, so I'm going to add in some grid line and also the grid point. Okay. Suppose the temperature along the boundary of this thin plate is known, given to you. Yeah. So this is so-called boundary condition. Yeah. So when we know the boundary, is it possible for you to determine the temperature within the plate itself, anywhere? So this is what we call the temperature distribution problem. Okay. So I want to illustrate, suppose we zoom into these 4 internal nodes, T1, T2, T3, T4. How do we find the temperature? Now, suppose I change the boundary condition. All the 4 sides are of the same temperature. Then, of course, you know the answer straight away, right? Because in the steady state, the temperature will be all the same everywhere. And that is a not interesting question. But now we have a slightly more complicated situation. The boundary, the 4 boundary, all different temperature. Yeah. So what we are going to do is to see how we use linear algebra to solve this problem. But we need to borrow some fact from physics. So the temperature at any particular node is the average temperature of the neighbor. You take the left, right, top, bottom, and then you average it. Understand? So let's see how we turn this into a linear system. So node 1, T1, what do? We look for its neighbor. It has 4 neighbors, right? So that means T1 will be just look for 10, 20, T2, T3 divided by 4. Now you notice, I still cannot solve T1, isn't it? Because this equation involves T2 and T3, which is also unknown. You get the idea? Right? So we can only use this as one of the equations, and then hopefully we can have some other equation together and we solve it as a system. All right? Okay, I'm sure you can make this equation nicer. Okay, right? We bring the 4 over and then we bring the T2, T3 over, all the unknown on one side, or the constant term on the other side. Yeah, I'm sure you're all expert in doing this. Okay, so that is the first equation coming from T1, from the node T1. Then let's move on to T2. Do the same thing, right? Get all the 4 neighbors, right? Take the average, then you come up with another equation. Yeah. So you do this for T3 and T4 as well, which I will not go into details, right? And then you can set up 2 other equations. None of the equation by itself allow you to solve for any of these unknowns, but collectively, this becomes a linear system. And when you take linear algebra, we will teach you how to solve this in the systematic way. Okay? But I'm not going to solve it now. If you're interested, you can bring this back and solve it yourself. Okay. Now, it's actually also very important that you try to link up the 3 different mathematics objects together, right? So this is a linear system that I showed you just now, right? With 5 equations, 4 variables. We call this the standard form of the linear system. Now, in linear algebra, we are going to introduce to you or explain to you that this linear system can actually be put into something called the matrix equation form. Now you see, I turned the original standard form into one big matrix that contains all the coefficients. And then there's a vector x, y, z, w, which contains all the variables, all the unknown. And then I equate it with another vector which contains all the constant terms, right? So we call this a matrix equation form. So you see, initially it's a linear system, but I can actually associate it with a matrix with vectors. So everything come together. The fun part about linear algebra is that you're going to see a lot of connection, right, between these 3 objects interplay. All right, here's my second example. Let's say you are a manufacturing company. You want to produce 3 objects ABC. Yeah, you are the boss. So there's a lot of things for you to consider. One of them is, of course, the production cost. Okay, so here is a table that breaks down all the different parts of the cost. You have the raw material to consider, you have the labor, you have the other miscellaneous things. So you have these 3 components and you have these 3 products, then naturally you are going to set up a table like this, isn't it? A 3 by 3 table. And naturally this 3 by 3 table can be turned into a matrix, a 3 by 3 matrix. And in this case, in finance or econs, we call this production cost matrix. Yeah, all the numbers in it has some meaning in this context. Now, not only is it more natural to translate the table into a matrix, rather than put all the 9 numbers all along the same line, yeah, but it is also easier for you to do manipulation, to solve the problems, related problems in an easier way. Okay, so I'm going to show you, illustrate to you. So it's the same setup as just now. So now you are the boss, right? You decided to produce 3,000 units of product A, 2,000 units of B, 5,000 units of C. And you want to calculate how much does it cost. Yeah? So how can you make use of this production matrix? Well, you just use the 3,000, 2,000, 5,000, make it into a vector. Yeah? And then put it side by side with the production cost matrix. So those of you who know matrix multiplication, you know you can perform this operation. And the outcome is equal to this. It's just something very straightforward, huh? But just for the sake of those who have not done matrix multiplication before, what do? We take this number, multiply by this as a pair, right? Then we take the second number, multiply by this second number in the vector. And then finally, this number pair with this number, multiply. So we have 3 pairs of product, right? And then we add them up. You sum it up, it's going to give you 1650. Then you do it for the second row and the third row respectively. Yeah, multiply with the column vector, you're going to get the output. Okay. So what does that mean? Well, you're going to see that we are not just doing a mathematical problem, multiplying exercise. Okay, it actually has meaning, right? The product of these 2 matrices, yeah, is equal to the outcome is actually tells you about the total raw material cost to produce all the 3 types of product, right? Total labor cost, total overhead cost. Yeah. So you see, by using a matrix, the multiplication is easier. Now, suppose now I give you a reverse kind of problem. I don't consider how much I want to produce. I want to first ensure that if I'm given this amount of resources, yeah, if this is what I have, this is my budget, how much can I produce for each of the 3 products? So how do we solve this one? So this time, the number of items we produce for ABC is unknown. So let me just call it lowercase a, b, and c, right? Using the same idea, if we multiply the production cost matrix to ABC, it must give me the total labor cost, total raw material cost, and total miscellaneous cost, right? So that's why we equate this matrix equation to the given budget. Then we try to solve for A, B, and C. So it's no longer just multiplying matrix. Huh? You are actually solving a matrix equation. The unknown is stuck here. Now, if this is a simple equation like 3x equal to 5, then very easy, right? How do you find x? You just bring the 3 over to the right-hand side. Is it? So x becomes 5 over 3. 5 divided by 3. Can I do the same for a matrix equation or not? In fact, you can, you know. So let me erase this. So actually what you see here is a linear system in a matrix equation form, isn't it? Which is what I showed you earlier on. But based on what I just said, trying to bring the coefficient over to the other side, you can do it. You can actually, there is something called the inverse of the matrix that allows you to bring the entire matrix all at once to the right-hand side. Then it becomes the inverse. So again, this is something that you are going to learn in the linear algebra course, the inverse of a matrix. Okay? All right. My second last example, population model. Okay, so we use linear algebra everywhere. So this is a very simplified version of a population model. So let's say in a certain town, we classify all the women into married women versus single women. And you are given that every year, 30% of the married women get divorced and become single. And 20% of single women get married and become married women, of course. Okay? So this is a condition given to you. And then you're also given that initially there are 8,000 married women, 2,000 single women. Okay? So the question wants you to find how many married women and how many single women will there be after n years. Yeah, this looks like a very simplified math problem, right? But it's just for the sake for me to illustrate to you. In real life, when the government and whoever doing the planning for the nation, right? They really have to set up a more complicated model for the population. You understand? Okay. Now, if you don't know linear algebra, how are you going to solve this one? Let's say we don't do n years. We do after 1 year. Can you find the answer? Should be, right? I mean, you just intuitively use whatever math knowledge that you have learned. You should be able to find after 1 year, how many married women and single women would there be? And then you can find after 2 years, after 3 years, right? One at a time. But in general, if I want you to find after n years, is there a more efficient way of doing things or not? Answer is yes, use linear algebra. So let's see, huh? So of course, when you do mathematics modeling, you need to set up equation. You need to introduce notation. And that's what you learn in mathematics. Huh? So for the married woman after n years, which ultimately is what we want to find, I'm going to denote it by m sub n. Okay? And likewise, for single woman after n years is s sub n. Yeah? So you see, I'm using a slightly more complicated notation with subscript n to indicate this is after n years. Okay? Then, so this is the slightly harder thing, huh? But I hope you can appreciate why this is the case. So I'm going to set up an equation that compare two consecutive years. You see, left-hand side is subscript n, right-hand side is subscript n minus 1. That means 1 year before that. Yeah, n minus 1 year versus n year. So for two consecutive years, why is it 0.7? Because 30% of the married women become single. So only 70% of the married women last year will still remain as married this year. Make sense? And then also 20% of the single women will contribute to the married woman in the following year because 20% get married. Yeah. Now, and then on the other hand, you can also set an equation for Sn for the same reason. I'm not going to go into detail. Okay. So again, you have something like a linear system, except that this one is to describe a population model. And again, you can turn this standard form into a matrix equation form. You see, now this becomes very nice, isn't it? The left-hand side is the population after n year. The right-hand side is the population after n minus 1 year. So in other words, you have a very nice equation that compare the population between two consecutive years using a matrix. Okay, let me further go on. So after 1 year, yes, you can use your elementary method to find the population. But now I want to illustrate, you can actually use the original population, 8,000 and 2,000 married versus single woman as the initial population, right? And you just multiply this matrix that we have found in the previous slide. That will give you the population after 1 year, isn't it? Make sense? Because it's like year 0 versus year 1. Huh? So you can easily multiply. If you know how to do matrix multiplication, you can easily find the answer 6,000 versus 4,000. Right? After 2 years, no sweat. Right? You can do the same, use the same matrix again, but this time multiply to population after 1 year. 6,000, 4,000, then you just multiply. And then you get the population for after 2 years. Alternatively, you can also start with just simply use the initial population. And then what you are doing is that you multiply the same matrix 2 times, isn't it? Yeah. So multiplying the matrix 2 times is like raising to the power 2. You square the matrix. So if you know how to square a matrix, then this can also be solved easily. So can you extend this in general? Yes, you can. After n years, you want to find the population after n years. Now it becomes very easy, right? You just take the starting population, keep multiplying the same matrix n times. You get an idea? So this matrix raised to the power of n, then multiplied by the initial population. You don't even need to step by step go and find the population after 1 year, after 2 years, until you reach after 100 years. No need, huh? Okay. Then somebody will ask, then this power n, how to find? Okay, so again, in linear algebra, when you study linear algebra, we will also introduce you an efficient way to find the power of matrix. Okay? This is my last example, a famous example. Everyone knows Google, right? You use Google as a search engine. Okay, so the basic idea of this Google search engine is that it will generate, you will try to search, right, all the keywords and then find the relevant web pages for you. Okay, but the more important feature is that it is also going to rank all the web pages. From the most important one will be ranked higher, less important will be ranked lower. Okay, so how does Google do it? Of course, now the algorithm behind Google is very complicated now. But basically, it actually looks for the hyperlink. What do I mean by that? So I'm just going to illustrate using a very simple 4 web page example. Okay, suppose there are only 4 web pages, A, B, C, D. Yeah, and then this is going to translate into a 4x4 matrix. So imagine if you have a 100 web page, then you are talking about 100 by 100 matrix. Yeah, but here is just for illustration, 4x4 matrix. Okay. So the 4 rows and 4 columns corresponds to the 4 web pages, ABCD versus ABCD. How do you come up with this number? So the simple guideline is the following. We put in the columns, we do this column by column. Let's say web page A has a link to web page C, but it does not link to B and D. So the first column will look like this. I think it makes sense, right? So it has no link, so it's 0. It has a link, we put a 1. Okay? So this is how we form the first row, the first column of this link matrix. Now, suppose web page B has a link to A, B, and C, all the other 3 web pages. So we don't put 1 because it is shared by the 3 other web pages. So it becomes 1/3, 1/3, 1/3. You get the idea? Okay? So now you understand. So for C, it has a link to A and D. That's why A and D will share half-half. Okay? And finally, D also have a link to B and C. So B and C is half and half. So the idea behind Google page rank is that more people link to your page. That means you are more important. Does it make sense or not? Okay? So based on this, intuitively, can you tell which one is the rank highest? Which one should be rank number 1? I'm sure you have some answer. So we are going to see how linear algebra can come in. Now in linear algebra, there's an important concept called eigenvector. So of course here you do not know how eigenvectors is derived, but you'll be taught in linear algebra course, right? So the eigenvector, yes, this is how a vector looks like. But yeah, this vector, actually, the numbers correspond to the ranking. The higher the value, the higher is the rank. Okay? So the page rank in this case, C will be the rank highest. I'm sure it's expected, right? And A and D are tied. Yeah, based on this scenario, A and D are equally important. Yeah, and B rank the lowest. You may say that, well, I can do this by intuition. Well, of course, 4x4 is easy for you to see intuitively. Yeah, but in this case, if it is a 100 by 100 matrix, it's not so easy for you to see. So you need the help of eigenvector. Okay, so I've come to the end. I'm hinted by the MC that I'm running out of time. So I probably can entertain a few questions. Yeah, but here the small QR code is for you to type in your Q&A. The bigger one is the mathematics department website if you want to find out more information. Okay, so I think I will stop here. Thank you. Okay, never mind.
Okay, thank you, Prof Tan, for guiding us through this masterclass. Unfortunately, it seems as if we don't have questions. We don't have time for Q&A for the moment. However, you may send in your questions at the email address shown here on the screen. If not, how about Prof Tan? Do you have any parting words for them? Any last words?
Okay, I apologize that I overrun my talk time. I've not been doing live lecture for very long, so get carried away. So anyway, if you have any questions, I will be outside, and maybe you can, if you really have some burning questions, you can ask me. Okay. Yeah. Thank you.
Thank you so much, Prof Tan. We have now reached the end of our masterclass on why is linear algebra important. We hope that you have been able to learn more about this course and enjoyed your glimpse into learning at today's Experience NUS Open House. There are many activities that have been planned for today on the campus, such as student life activities happening at UTown. We wish you a good day ahead, and please exit the lecture theatre via the door here on my left. Thank you.